So now we want to extend this framework to 2D problem. We noticed that by reviewing the literature review, all the previous works are solving the problems which is either subjected to a traction at the surface, or they are solving a problem where they have access to the first few snapshots of the wave propagation, and they are interested to see how these snapshots or wave propagation will be propagated in the future time steps. So for the first time, we are going to solve a problem where we have a localized feature, and we are going to consider the effect of remote excitation or far field excitation. For that purpose, we followed the DRM, but in the strong form of partial differential equations. Similar to the original paper of the DRM, similar to the original problem of DRM, we considered a problem where we have localized feature and we have a source of excitation. We decomposed this problem into two regions, and we wrote the equation, partial differential equation, for the inner part, interior part, and the exterior part. And again, similar to the DRM, we considered a free field problem. We considered an auxiliary problem where all the responses are based on free field responses. And again, we can decompose this system into two parts, and we can write the governing equation for the exterior part. So now we have the equation for the exterior part, both in the original problem and in the free field problem or the backend problem. And by knowing the fact that the responses are the summation of the free field and the scattered, we can subtract these two equations from each other, and we see only the scattered components will be shown up in the equation we have. So for the exterior part, all we have is the scattered component, but for the interior part, everything is based on the total responses. And now we can add these two subdomains to each other, and at the interface of these two subdomains, instead of having continuity of displacement and stresses, we have the jump conditions defined in these two equations. A similar notation can be found in the work of Bielak in 1984. So we said that we transform this original problem into a new problem where we have the jump interface, which is in charge of generating the incident waves or incoming waves. And in addition to that, we need to consider an absorbing boundary condition with some distance from this jump to absorb the scattered waves. And we are interested in general, we are interested in solving problems which the length of this exterior part is very small. The most optimum case would be the case that we place this absorbing boundary condition exactly on top of that jump condition. In that case, we have the transmitting boundary condition, which not only generates the incident waves, also it absorbs the scattered component, scattered waves. So we use the Leismer dashpots, Leismer absorbing boundary condition. With the information we had for the jump, we noticed that we can replace these terms with the information we have in the jump and propose our transmitting boundary condition for the Leismer dashpots. So this is the original problem. Instead of solving this problem, we defined three different configurations. And in the first configuration, this is the case where we have the transmitting boundary condition exactly at the interface of the basin or the localized feature that we have and the elastic bedrock. The second configuration is where we have a transmitting boundary condition within the bedrock at some distance from the basin. And the third configuration is where we have absorbing boundary condition, and we have a jump interface at the interface of the basin and elastic bedrock. So similar to the previous 1D case, 1D problem, we can write different loss terms for our configuration 1, which is the simplest case, and for configuration 2 and 3, because we have discrete change in mechanical properties. Again, we need to do the domain decomposition similar to what we had in our 1D problem. But in 2D problem, at the interface of these two subdomains, depending on either we are using transmitting boundary condition or absorbing boundary condition, we need to satisfy either the continuity of the displacement and the stresses or the jump condition. So let's start with the toy problem again. These are the mechanical properties we have for this toy problem. And these are the free field responses we have at gamma 1 at the interface of basin and elastic bedrock, the free field displacement and the tractions. And here we are showing the animation of how the wave propagates in the original problem and 3 different configurations we discussed before. As we see, the difference between configuration 2 and 3 is that in configuration 2, everything is based on the total responses, but in configuration 3, for the inner part or the interior part, everything is based on the total responses, but for the exterior part, everything, all we have is the scattered components. So let's see what are the errors for our finite element and pin for different configuration. For config 1, where we had TBC at the interface of basin and elastic bedrock, we see that the truncated finite element model has 25% error, which was expected because we are using the Leismer absorbing boundary condition, which is a first order local absorbing boundary condition, as TBC, and we don't allow the wave propagating in the exterior part. But for the pin, we see that when we compare the results of the pin versus finite element truncated, the errors are less than 6%, which is very similar to what we had for the 1D case. For configuration 2, because we are placing the TBC at some distance from the basin, we see that the normalized error for the finite element model is decreasing to 9%. And again, when we compare the pin versus FEM truncated, we see that the errors are less than 10%. And for the final configuration 3, because we are using absorbing boundary condition, we see the errors of the finite element truncated are less than 4%. And when we compare the response of the pin versus finite element, the errors are less than 8%, which again shows the promising performance of the pin. To check if the dimensionless equations are working in the 2D problem setting as well, we considered a more realistic problem with these mechanical properties. And instead of considering a homogeneous basin, we considered the VS profile changes based on this figure in the basin. And we are showing only the result of the configuration 3 because it had the best performance. We see that the errors of the finite element model are less than 2% in comparison to the original problem. And when we compare the response of the pin versus FEM, we see that the errors are less than 7%. Then we considered 11 points at the center of the basin at different depths or heights. And we plotted the displacement, velocity, and acceleration, similar to what we did for our 1D problem setting. And again, we see that pin is predicting the responses with very good accuracy. However, because we are smoothing, actually pin is smoothing the responses, we see that it cannot capture these frequencies. We have some errors in acceleration, similar to what we observed in our 1D case and when we plotted that response spectrum. So let's have the conclusion and see what are the capabilities and the limitations of each of these works. We started by considering a data-driven model. In that case, we showed how we can use the LSTM model and how we can modify the architecture of LSTM model to accept both time-dependent and scalar random variables. We showed that this forward LSTM model can be used as a forward model for the purpose of uncertain quantification, and it can capture the distribution that we are interested in. However, we noticed that the limitation of this work is that it is not good in doing post-processing, and every time that you want to predict a new quantity of interest, you need to change the training and train your model based on that new quantity of interest. Then we switched to the pins. We started by modeling the 1D wave propagation in a soil column, and we showed how combining different techniques such as dimensionless equations, transfer learning, domain decomposition, temporal domain decomposition, they can help us predict the long duration excitations. However, the limitation of this work was that because the pin cannot capture high frequencies, we noticed some discrepancies in the acceleration and the response spectra of that one. Then we switched to the 2D problem. We extended our pin to the 2D problem setting. We showed how we can follow domain reduction method in a strong form and how we can present the jump conditions in the strong form of partial differential equations. Then we presented how we can introduce transmitting boundary condition, and for that purpose, we used the Leismer dashpots. However, the limitation of this work was that because we used Leismer dashpot, which is a first order local absorbing boundary condition, we noticed that the performance of the TBCs are not good, but one can use higher order absorbing boundary conditions such as Clayton, which the performance is much better than the Leismer boundary condition, and generate new transmitting boundary condition. In that case, probably they should be able to see the errors for all of these configurations should be the same. I should mention that implementing these higher order absorbing boundary conditions in finite element setting is really difficult. It's almost impossible. But the good point of PIN is that we can implement them easily within the PIN framework. So that's one of the advantages of using PIN. That was all. Thank you, Olaf. Thank you for attending this presentation. I would like to have, I know you are all waiting for me to mention your name, but I want to start with my advice. Thank you, Professor Seilabi, for your support and your encouragement. I'm really honored to be your student. Thank you, the committee members, for your comments, your feedbacks. I tried to implement all of them in my works, and thank you, all of my friends, excluding some of you. Yeah, that was all. Thank you.